If we talk about particle physics, this is the last topic of our A's syllabus over there. Here we will have to talk about the atomic structure or atom basically over there. Atom is basically, I can say, the smallest particle of matter, the smallest particle of matter is called atom over there. Atom is comprising the basic, if we talk about its basic subatomic particles, we talk about electron, we talk about proton, and in the last, neutron. Electron is negatively charged, proton is positively charged, and neutron is neutral. If we talk about their masses, then it is 9.1 multiplied 10 raised to power minus 31 kg. If we talk about mass of proton, we take it 1.67 multiplied 10 raised to power minus 27 kg. And neutron approximately 1.66 5 like that multiplied 10 raised to power minus 27 kg. If we talk about charge in coulombs for electron and proton over there, then we say electron is having negative 1.6 multiplied 10 raised to power minus 19 coulomb, also equal to E negative, and proton have the charge 1.6 multiplied 10 raised to power minus 19 coulomb, and neutron is having neutral or zero charge. Proton and neutron, these two are present in the tiny, very small in size nucleus of an atom. On the other hand, the electrons are present in the shells around the nucleus in which they revolve around nucleus over there. And if we talk about the nature of other radioactive substances like that, then we will also have to keep in mind that particle physics initially started with radioactivity. Radioactivity means the process in which the elements which have the atomic number which have atomic number greater than 82 are the radioisotopes of less atomic number, radioisotopes which are naturally unstable, which have atomic number greater than 82 are radioisotopes that are naturally unstable. They are continuously going to emit the radiations in the form of alpha rays, in the form of beta rays, and in the form of gamma rays, radiations to get stability. Over there. So this process is called radioactivity, and such materials are called radioactive substances, which we will have to take in under consideration over there. And if we go for discovery of little bit nucleus, talking about that, for example, I am taking here polonium as a source of alpha radiations or alpha rays over there. They are coming. And after that, I have a gold foil of thickness 0.0004 times 4 centimeter, then what happens that alpha particles mostly pass straight line over there, but only very rare means only from 20,000 there is a one ray which is showing little bit deviation or which is showing the repulsion in the totally reverse direction over there. Then I can say this type of uh, assumption shows that the alpha particle is deviated due to the repulsive force, which shows that nucleus has positive charge due to proton, as alpha rays or alpha particles are having +2 charge and are called helium nuclei. In that case, as they have shown some deviation due to repulsion of the charges, because same charges positive is going to show repulsion over there. In case of positive particles, alpha particles and protons, which are coming near to the gold foil of this thickness, then I can say gold foil, then I can say that they are showing the deviation due to the same charge. And most of the alpha particles also very little deviation over there. So most of an atom is empty, because I said plenty of rays will go straight line. Then we can say it is most part of atom is empty. Most part of atom is empty, means not showing any type of place available over there. And a very few alpha particles are deviated at 90-degree or 180-degree reverse back over there, which shows that atom has a very small nucleus, very tiny, thick nucleus present in the center of the atom over there. And this was directly related to Mr. Rutherford for showing this all possibilities of the atom over there. After that, if we talk about nuclear density or something like calculations, then we can say that can be taken by the formula density is equal to mass over volume over there. And if you are going to calculate the nuclear density, then you remember that overall mass of proton should be taken and radius should be taken. Then radius is having the volume of the sphere 4 by 3 pi r cube. I will get the volume. And for mass, I simply said 1.67 multiplied 10 raised to a minus 27. And then by taking these mass with the multiplication of total number of protons and neutrons will be being multiplied with the mass of one proton or one neutron, then total mass can be obtained. And from the radius of that proton or neutron, I can calculate the density of nuclear density of the nucleus. Nuclear density can be easily calculated by that formula, but it is doesn't require. I just simply told you how to go with the shape of the molecule as like a sphere, as like a small ball over there. In case of nuclear density, nucleus over there. Then we will have to move towards nucleons and electrons over there. Nucleons, nucleons. Nucleons means protons plus neutrons, which are present inside the nucleus, are called nucleons over there. And on the basis of nucleon, we can explain the atomic mass, which is shown with the capital letter A over there. After that, there is atomic number or proton number. Atomic number or proton number, which shows with the help of proton or number of protons or number of electrons inside a neutral atom, we will have to take proton and electron in both cases. Then we can say atomic number is represented by capital letter Z, and in the periodic table, if you want to show some element over there, then atomic number will be below and atomic mass will be written above of the element over there inside the periodic table. And when we are talking how to calculate the number of neutrons from the atomic mass and atomic number, the number of neutrons will be obtained after subtracting atomic mass with atomic number. Then I can calculate what is the number of neutrons present over there. After that, we will have to move towards the isotopes. Isotopes are the atoms of an element. Isotopes. Isotopes are atoms of an element, atoms of same element which have same atomic number, but different atomic mass, are called isotopes over there. For example, if I am taking isotopes of hydrogen, isotopes of carbon, oxygen are like that. Hydrogen H11, hydrogen 1,2, hydrogen 1,3. Hydrogen 1,3. Hydrogen 1,1 is named as protium. Hydrogen 1,2 named as deuterium. 1,3 is named as tritium. Protium, deuterium, and tritium tell us that this hydrogen has one proton, one electron, and zero neutron. One proton, one electron, and one neutron. One proton, one electron, and two neutrons. So, as we know, proton and neutron sum will give us atomic mass, and for the same hydrogen element, the mass of that atomic mass is changing, but atomic number of protons or electrons are staying the same over there. It's the same case, carbon 12 with 612, carbon 613, carbon 614 are also being taken. Protons, 6 electrons, 6 neutrons. After that, 6 protons, 6 electrons, and 7 neutrons over there. And I can also say here 6 protons, 6 electrons, and 8 neutrons. Again, the mass number is changing and isotopes can be elaborated over there. So isotopes are the nuclei of same element with different number of neutrons, but same number of protons over there. So keep in mind the relationship between the isotopes and their uses will also be changed depending upon the main structure of the forces. After that, there are basically two, if we talk about basic forces of nature, basic forces of nature over there, then I can say here, there are basic 5 main forces. Number one is electric force. The force which is present between two positive or negative charges over there in the form of attraction and repulsion is available. Number two is gravitational force, means the force which is available for the attraction of one big masses to the small masses over there is called gravitational force, and gravity of earth like that. Number three is magnetic force, which we can say between the north and south pole, the north and south attraction, north repulsion, south repulsion forces are available. At number 4 is weak nuclear force. Weak nuclear force is that which nucleus is exerting on the shells of electrons. Shells of electrons, then that is called weak nuclear force. And the strong nuclear force, strong nuclear force means the force with which protons, even though we know there is a positive charge on proton, how the protons are in a tiny nucleus being properly tightly packed over there to give you a tiny nucleus over there. Strong nuclear forces are responsible for that purpose. So we can easily say that these are the 5 basic forces which are present over there in nature. So I will have to move towards now the fundamental particles over there. If I talk about fundamental particles, then there are 2 basic families of those particles. Fundamental particles. Then in case of fundamental particles, now I am going to talk about proton, neutron, and electron over there. How can we go for judging it? We can simply say here that subatomic particles are divided into 2 main families. Number 1 is related to hadrons, and number 2 is related to leptons. Hadrons is having neutron, proton, are there anti-neutron, anti-proton like that will be available. In leptons, there is electron basically mainly available in this family over there. The hadron words basically coming from bulky. This hadron means bulky, means mostly mass is being carried out by these nucleus over there in the form of hadron, and on the other end lepton means light. Light means light in weight, light in weight, and when they are jumping from one shell to another, they are going to release the energy which is having different frequencies over there. When we are going towards hadrons in details, then we can say there is uh, basic corresponding phenomenon that is related to quarks over there. Quarks are basically up, down, strange, and pi. All of these are the quarks which we will have to take into account. And up, down, strange quarks are being used to represent our basic fundamental particles, which is related to proton. Proton is basically having up, up, down as the quark structure. On the other end, if I talk about a neutron, then we can say up, down, down quark should be taken into account for neutron. And if I am, and these two, which are made up of with the help of 3 quarks in both cases, are called baryons. These are called baryons. These are called baryons. On the other hand, if I am saying that the 2 quarks are available and they are making some particle that is called mesons. Mesons, if we give the example over there, that is pi plus meson, pi plus mesons. If I talk about pi plus mesons, then it is made up of 1 up and 1 anti down over there. When I use word anti, then I will give a small win column over that quark over there. Or we can say phi meson. This is pi meson. If I take phi meson, that is also related to a group which is having the meson clause, in which 2 quarks are used for showing that fundamental particle over there. then I will say here 1,5 meson is going to be formed with the help of 1s strange and anti-strange should be taken into account. Then 5 meson is going to be formed over there. If we talk about the charges on these particles of phi positive, phi negative over there, we will also be taken into account these formations on the basis of quarks over there. And if I say that this is mesons and anti-mesons over there, then how can we calculate the elementary charge over them? For that purpose, I will say here that the charges are given in the form of fractions like up, down, up, down, up, down, up, anti-up, down, anti-down, strange, anti-strange over there. For these values, we will have to use the main form in which we can say okay, here we are going to put all of those values of their charges so that how can we get the elementary charge over there. For up, there is a charge plus 2 by 3. Anti-up will be definitely having the charge in opposite form with minus 2 by 3. Minus 2 by 3 over there. And if I'm talking about down over there, then this charge is minus 1 by 3. And if I'm taking anti down, then it is 1 by 3 over there. If I'm taking a strange over there, then remember that strange is having the charge exactly like down over there, minus 1 by 3 and 1 by 3 should be taken into account for strange over there. And if I am going towards more their top and bottom is also being taken over there, then there is another top and bottom. Top is having the charge like up, then it is plus 2 by 3, plus 2 by 3. And if I take anti-top, then it is minus 2 by 3. Bottom is having the charge just like the down over there, that is minus 1 by 3 over there. So these are the charges which should be taken as the normal up or anti-up, down or anti-down, strange or anti-strange. All the charges should be taken out to calculate our elementary charges on electron, proton and neutron over there. If I go for electron, proton and neutron, then I can simply say here that the electron, for example, I am taking the neutron over there. Neutron, I said it is will be made up of up, down, down quark. Now, up is having the charge plus 2 by 3, plus 2 by 3, plus down is also available over there. Then it means it is minus 1 by 3, means it is minus 1 by 3. Another is the down also, then it is also minus 1 by 3, giving us the total net charge as 0. So the charge on the neutron is 0 by shown with these elementary charge particles over there to be taken into account. After that, if I go for this proton over there, then we know that the proton is made up of up, up, down. Then it is plus 2 by 3, plus 2 by 3, minus 1 by 3. So it is 2 plus 2 minus 1 over 3 is equal to 4 minus 1. 3 over 3 will give us 1. So this is the charge on the proton to calculate out by the elementary charges of the basic quark particles over there. After that, if we go towards the properties of ionizing radiations and how they are going to be changed when they are being converted by alpha decay, beta decay, and gamma decay, how they should be going to be taken into account. Then I am telling the last thing in this topic over there, that there are radiations, alpha radiations, then there are beta radiations, and in the last is the gamma radiations. Alpha radiations are basically helium nuclei. They are made up of two protons and two electrons having the charge of plus 2, and their mass is 2 proton, 2 neutron. Like helium nuclei, I will say it is a 4 atomic mass unit, unified atomic mass. And due to this large mass, they show a very less penetration, like even in the air, penetration, even we can say they are having a very less penetration when they are passing through the air over there, and that can be taken in the form of few centimeters over there. But when a page is coming in front of it, like a book page over there, they are easily stopped by them. And if we place these alpha particles in an electric field, they will be directed towards the negative plate of the electric field over there. And we can say here that alpha particles may show very less penetration, and they can show very strong ionization over there. And after that, there is strong ionization of alpha particles. If I go with the beta particles, and if alpha radiation is emitting from some element, like I say, X is an element, I have atomic number, let's suppose Z, and atomic mass as A, and when it is converted into product Y like that, then I will say here that the atomic number will be decreased by 2Z minus 2, and atomic mass will be decreased by 4 number over there, and you will get some alpha particle of 2 4 as in the form of chemical equation over there. On the other hand, beta radiation is of two types, and if I talk about its nature, then these are electrons. And if we talk about electrons in the form of beta radiation, we can simply say here that these beta radiations are showing more penetration than alpha particles. But less than gamma particles. Over there. And if I say what will happen, then beta positive and beta negative decay are available. Beta positive. In case of beta positive, if you are taking an element X over there with atomic number Z and atomic mass A, and you are producing beta with the plus 1 and 0 above, then we can say here that atomic number is, here it is plus 1 to show beta positive decay. Then I will say the new element which will produce in the form of Y will have Z minus 1, and atomic mass will stay as it is. A will remain, A is over there. After that, if we say that it is beta negative decay, if I say it is beta negative decay, then I will say, for example, I'm taking element X with atomic number as Z and atomic mass A, then I can say beta negative is going to be produced on the other side, beta negative and 0 plus. It means that our beta negative decay is going to show the phenomenon of atomic number to decrease by 1 is done. Now it is going for -1. Now it will have to increase. So it will be Z plus 1 with respect to atomic mass as like A as it is. And if we go for gamma radiations, we know that they have no charge, no ionization at all, no charge, or we can say no charge it have. They are not affected by electric field or magnetic field over there. They move a straight line, and they can easily be showing the high penetration over there. High penetration. High penetration over there. Penetration. High penetration, low ionization. Low ionization, high penetration can be taken into account for explaining all of these values of alpha, beta, and gamma. And if I write about its equation, which is related for gamma decay over there, if I say there is gamma decay, then remember that the element which is showing in the form of X as the element, this X is already having a very large quantity of that material over there. So gamma decay will have, for example, atomic number Z, atomic mass A, and having some high kinetic energy. What is going to happen that it will be uh, having atomic number as it is, atomic mass as it is. Just it should be like atomic number, atomic mass, and gamma particle. Atomic number and atomic mass in case of gamma decay will not change at all. So this was a chapter completely being told to you, which was having the alpha particles, beta particles, and how much they are penetrating over there. And a radiation is absorbed by a thin sheet of paper on few centimeters of air, then it will be helium or alpha particles. Beta radiations is absorbed by few millimeters of metal because they have more penetration as compared to the outer layer. On the other hand, gamma radiations is never completely absorbed, but a few centimeters of the load and several meters should be being taken in the form of complete work over there. So we can say here that it should be taken into account by summarizing all of this lesson. This was your particle physics, which he will ask by all of these questions. So not to worry, it is easy topic. Just revise it and you will assemble it. Okay.
जी सर